Alright, hello, my name is Michael Waters, and today me and my group are going to be presenting on solar energy in space. Alright, so first off, we'll go with a little bit of an introduction. So, solar energy is the radiation that comes from the sun, and we convert it to electrical energy using devices called photovoltaic cells. These cells are usually made from silicon, and when the sunlight hits them, they release electrons, which creates an electrical current. They're completely solid-state devices, so there are no moving parts. In recent years, solar technology has been improved significantly, and we've seen a big increase in its use on Earth. But in space, solar panels are even more useful. They give spacecraft a steady, reliable power source, which is very important for long missions. Batteries also can't last for very long, especially on something like a deep space probe, so often solar is one of the more realistic options. In this presentation, we're going to cover 5 main topics. First, why solar energy is used in space, then the current applications of this technology, the technological challenges that it faces, the concept of space-based solar power, and finally, we'll touch on some ideas for the future of solar energy in space. Alright, so one of the biggest advantages to using solar energy in space is that there's no atmosphere to get in the way. On Earth, the atmosphere reflects approximately 30% of the light that hits it, so solar panels here never get the full amount of energy that they can potentially receive. In space, that's not a problem. Solar panels can receive much more sunlight, and that leads to higher efficiency. Also, solar panels aren't affected by clouds, weather, or pollution if they're in space. On Earth, bad weather can cut power generation significantly. However, in space, the conditions are much more stable. Another big advantage is the continuous exposure to sunlight. If you place solar panels in the right orbit, such as geostationary orbit, they can face the sun for up to 24 hours a day without ever experiencing the night. That kind of power supply is a huge benefit, especially for satellites and space stations. Overall, solar power in space is more consistent, more efficient, and more reliable than it is on Earth, which makes it ideal for powering everything from communication satellites to interplanetary probes. Alright, so now we're going to move on to some of the current applications, one of the most well-known being the International Space Station. So the ISS uses 8 massive solar arrays to generate approximately 120 kilowatts of electricity. This energy powers everything on board, from the life support systems to the lights to the scientific instruments as well as the communication equipment. The station's orientation is constantly adjusted to maximize sunlight exposure, and astronauts have even conducted spacewalks just to maintain or upgrade the solar panels. Another great example is the Hubble Space Telescope. Although significantly less power hungry than the ISS, the Hubble still has 2 solar arrays to supply power to its onboard systems. These include the high-resolution cameras and data transmitters that send all of those amazing deep space pictures back to Earth. The energy from its panels are also stored in batteries so that it can operate when it's in the Earth's shadow. And then the third example that I want to talk about is the NASA Juno spacecraft, which is currently orbiting Jupiter. So what makes Juno so unique is it's the first spacecraft to operate so far from the Sun using just solar power. Jupiter is approximately 5 times further from the Sun than Earth is, so sunlight there is about 25 times weaker. To deal with that, Juno has 3 large solar arrays, which are all about the size of a school bus. Despite the low light levels, they generate enough electricity to power the spacecraft, scientific instruments, and communications. Juno shows how far solar technology has come, making it possible to explore deep space without relying on nuclear power.
Space-based solar power, or SBSP, is a revolutionary idea that involves placing solar panels in orbit to collect energy directly from the sun. Unlike Earth-based systems, these panels are exposed to constant sunlight, avoiding weather, atmosphere, and the day-night cycle. That means we can generate power 24/7 with far greater efficiency. This energy could then be transmitted wirelessly to Earth, reaching even remote or disaster-struck regions. As global energy demands increase and the climate crisis worsens, SBSP presents a sustainable, long term solution for clean, uninterrupted energy generation. Space based solar power, or SBSP, works by placing large satellites equipped with solar panels into geostationary orbit, about 36,000 kilometers above the Earth. These satellites collect solar energy continuously because there's no atmosphere to block sunlight and no nighttime in space. The collected solar energy is then converted into a form that can travel through space, usually microwaves or lasers. This energy beam is then aimed at a receiving station on Earth, where it's captured by a special antenna called a rectenna. The rectenna safely converts that microwave or laser energy into usable electricity, which can then be fed into the power grid like energy from any other source. This system has the potential to deliver clean, renewable power 24/7, regardless of time or weather on Earth. Types of space solar power systems. NASA has explored two main approaches to building solar power satellites. The mature planar design is the more conventional one. It uses large, flat arrays, think of giant solar panel in space, that converts sunlight into energy and beam it down to Earth. It's reliable and well understood, but these structures are massive and difficult to launch and assemble. The heliostat swarm concept, on the other hand, is much more futuristic. It involves a swarm of many small, Mir-equipped satellites. These heliostats fly in coordinated formation and redirect sunlight to a central power conversion unit. This makes the system modular, more fault-tolerant, and scalable, like building with Lego blocks in orbit. However, it also requires advanced autonomous coordination and AI, which is still under development. Both approaches aim to achieve the same goal, constant space-based power, but they differ significantly in structure, complexity, and scalability. While the concept of space-based solar power is promising, building and operating is incredibly complex. First, launching the hardware is expensive, especially the large solar arrays, which could weigh tons. Then, the energy collected in orbit has to be converted and transmitted to Earth, usually via microwave or laser beams. This transmission must be safe, precise, and efficient. Any misalignment could mean lost power or safety risks. Next, the system must manage extreme temperatures in space. It must not overheat in the sun or freeze in shadow. Assembling or repairing these structures in orbit is also a challenge. Human crews may not be practical, so we may rely on robotics. Coordination is another issue, especially for concepts like heliostat swarms. Those would need autonomous control systems using advanced AI. Finally, all these components must resist the harsh space environment, debris, radiation, and mechanical wear, while still working reliably for decades.
So, I want to talk about the future of solar technology in space. And first, I want to talk about the solar cells. Um, so, what are solar cells? Solar cells use sunlight pressure for propulsion. Photons from the sun push against the large reflective cells to move the spacecraft. And this method helps to eliminate the need for traditional fuel and allows the spacecraft to have a longer and more sustainable mission. NASA has a solar cell system called ACS-3, or NASA's Advanced Composite Solar Cell System. It was launched in April 2024 aboard Rocket Lab Electron rocket from New Zealand. It utilizes a CubeSat with composite booms made from flexible polymer and carbon fiber. The cell can span 860 square feet, which is around 800 square meters. It was successfully deployed in the low Earth orbit. and that demonstrates the viability of the solar cell technology. Um, the key innovations are the lightweight materials. Composite booms are lighter and stiffer than the previous designs, which improves the stability. The compact storage booms can be tightly rolled and unrolled without significant bending, and it's really important for small spacecraft. Um, Also, um, it had an efficient deployment. Onboard cameras could ensure that the cell's symmetry, uh, that the cells is symmetric and have a proper shape during the deployment. Why it matters? It reduces costs. Um, it eliminates the need for heavy propulsion systems, and overall, it reduces the mission costs. Um, for extended missions, it enables the longer duration missions without the need for refueling, and it's also good for deep space exploration. That paves the way for mission to the moon, Mars, and beyond using the solar propulsion. So, the next one, let me see. The next one is for advancing the lunar solar power of NASA's Vertical Solar Array initiative. So, NASA selected three companies: Astrobotics, Honeybee Robotics, and Lockheed Martin, to develop an advanced vertical solar array for using on the moon. These arrays are part of the broader effort to establish the long-term human presence on the lunar surface. So, what are the objectives? The arrays must meet several challenges. They need to be stable on an uneven lunar ground. They should resist damage from the moon's sharp and sticky dust. Um, they should pack into a small volume for launch. Um, and they should automatically deploy once on the surface. These features are critical for remote and unmanned for remote and unmanned setup and reliable operation. So we need these um, to basically operate them the way that we want. Um, the funding and timeline. NASA is investing $19.4 million into these designs. The goal is to have operational system near the moon, near the moon's south pole, by the end of the decade, which is an area that receives near continuous sunlight, making it ideal for that solar power. So what makes it significant? These arrays will supply essential electricity for everything from the lunar habitats and vehicles to scientific instruments, which are which makes them which make them a key part of the NASA's Artemis program, and that aims to create a permanent human and robotic presence on the moon. Thank you for listening, and I think this is the end of presentation.